Your bell work. Follow the procedure. Don't worry so much about everything except following the procedure straight away. Just going step by step by step. So, how much force is needed to move a 1,200 kilogram piano, constant velocity across carpet? I give you a coefficient of friction. Force is applied downwards at a 15-degree angle. Now, whenever you're moving a big piano, I hope you don't push with any angle. Now, naturally, you're going to be a little bit taller, and so you're going to want to push with an angle. But whenever you encounter something really, really heavy, what do? You get down with it, parallel, and you push that way. Because, thinking logically, friction is equal to what? What's the equation? Mu times normal force, and normal force is the force that keeps you from pushing the piano or whatever, it falling through the surface of the earth. So whenever you push down, you're adding more normal force back up, making it harder to push because mu times normal force, you get more friction. Okay, that's why you get down. You naturally know I need to get down and push parallel. All right, so we already know this person isn't very bright. They're not pushing parallel. They're actually creating more friction. Thus, it's going to be harder for them to do. Step 1, draw a picture. I'll skip that. Step 2, free body diagram. So what forces do I have acting here? Normal, gravity. What else? Push. Which way is it going?
Down
Right.
15 degrees. Negative 15.
That doesn't matter.
FP and
Dispersion.
which way?
Left side.
At an angle or straight back?
Straight back.
Straight back is correct. Reason it's straight back. You can remember for me, please. Opposite the direction of motion, not up into the air, right? Opposite the direction of motion. Next step, what is it? Break into components. How many of these things do I have to break into components? Just one of them. Normal, gravity, friction. What happens to the force of push? Right on the X becomes what? How about on the Y? Good. 1, 5. Now, some people ask, well, how do I know which axis to put it on, which direction to go? Just use your common sense. The force is pushing down and to the right, according to your free body diagram. So the X is going to go to the right, and the Y is going to go down. I mean, so common sense should just be able to get you that far. Right.
Why do you not use 90 minus 15? Do you have to use a reference angle?
Use the angle measured to the x-axis. Okay?
Which doesn't make sense to me if you use 15 to 171 and use the y-axis to the y.
Always use to the x-axis. Always use to the x-axis because sine and cosine are built around, that standard sine and cosine are built around x-axis angles. Okay? Whenever you hit the y-axis, sine and cosine actually flip-flop on, which is what happens, and we'll get to this whenever you tilt your axis. We're getting there. Now, next step, what is it? Positives, negatives, right? Which way do you want to do positive and the y? Okay, I think you already answered my next question too. All right, so there we go. Next, as y'all said, x and y axis. So I'm going to scroll down a little bit. That way I've got room to do this. In the x-axis, sum of the forces equals ma. And in the x-axis, we had Fp cosine 15 minus the force of friction equals ma. Let me go ahead and get the y-axis set up for us too. In the y-axis, what's positive? Normal. What's negative? And
sine of Fp sine 15.
good. So I got normal minus Fg minus Fp sine 15 equals ma.
Wouldn't it be negative 15? No, because that minus negative.
Yeah, good point. not negative 15. The reason for it is we don't want to undo what we've already done. Okay? We're dealing with directions manually, thus the negative out in front, negative FP sine 15. If we make this a negative 15 degrees, right? The sine of negative 15 is going to be a negative number, right? Well, then a negative times a negative makes this thing a positive, and positive's going up, and this force shouldn't go up, it should go down. Right? So just use 15 degrees, that way you don't undo what you've already done. Okay? All right, pick an axis for me to start working in. X, sure. FP is what I'm looking for. Cosine 15 minus, what's the equation for friction? Mu times normal force. Okay. What's the acceleration here?
0.
How do you know? Problem said constant velocity. Good. So from 0 on that entire side. And AK said that we know our mu. What is it? Can I do anything else with the x-axis? No, I'm stuck. I can move it over if you'd like me to, but it's not a big deal. Right? I'm stuck. I have two variables. So what do I need to do? Go to the y. Just jump to the y. Normal, don't know anything about that, minus mg minus fp sine 15 equals, what's the acceleration?
0.
0. Object isn't flying up into outer space, plunging down to the depths of the earth. 0. All right, let's plug in what numbers we can. I got normal minus, the mass of this thing is what? 1200. Gravity, 9.8 minus fp sine 15. All right. Once again, don't put the negative inside of things, like negative 9.8. We use the negative. All negatives are is to indicate direction, right? If you make this negative 9.8, negative times the negative you already put on it, say that it was going down, makes it become positive, which means up, right? Exactly. The negative sign out in front, the subtraction sign out in front, takes care of direction once and for all for you. Okay? I mean, I can work a little bit of math here, but I already see a problem arising. What's the problem on the y-axis? Two variables. What does this mean? This is a system of equations. Look at the x-axis, at P and N. Look at the y-axis, at P and N. Pick one, solve for it, plug into the other. I'm going to use the y-axis, I believe, right now, since we're already working on there. Another suggestion for which variable to pick. Variables that are all by themselves are always the easiest to pick to solve for. Always the easiest. Normal force here is all by itself. It will be by far the easiest to solve for because all I have to do is move the other stuff to the other side. N equals, add my 1200 times 9.8 to the other side. Right? So now I've got a positive 1200 times 9.8 and add my FP sine 15 since we're taking subtract of the opposite. Right? So add that over to the other side. Plus FP sine 15. Let's simplify that down a little bit. What's 1200 times 9.8?
1,001 or 11,760.
Okay. Now I'm going to take that entire thing and I'm going to plug in the x-axis for normal force. Then I have one equation and just one variable. I can solve for FP at that point in time. Let me, just because I'm going to run out of space, let me recopy that line down a little bit. So now I've got FP cosine 15 minus 0.48. Now, whenever you're substituting in, use parentheses. especially here, because you're going to have to distribute that 0.48. Okay? So parentheses, 11,760 plus FP sine 15, close parentheses, equals 0. Check out that line, make sure you understand how I got that. Right, at this point in time, you see that we have an equation, just one variable, FP. Don't get freaked out. Yeah, some people have said, oh, there's two FPs in there. So what? It's like saying there's a 2x and a 3x in the equation. What's the big deal? What's 2x plus 3x? 5x. You can do the math then, right? As long as the variables are the same. Okay, so having 2, 3, 5, 205 of the same variable isn't a big deal. Just smush them all together and you're done, right? So now it's just smushing time. We got to distribute that 0.48. Good question. Yes, we're going to have to distribute that negative sign with it. The reason why you have to distribute is this isn't just 0.48 times 11,760.
Times the whole normal force.
It's times the whole of normal force, and the whole of normal force is 11,760 plus FP sine 15. In other words, it's 0.48 times each of those factors. Okay? So distribute these guys. Someone multiply for me 0.48 times 11,760.
5,644.
5,000 what? 644?
0.8.
0.8. All right. Plus 0.48 FP sine 15 equals 0.
Negative 4.8.
Oh, thank you. Must distribute that negative sign. Now in group-like terms, let me move the pure number to one side. All right, that leaves me FP cosine 15 minus 0.48 FP sine 15 equaling 5644.8. Now you have a choice. You can try to combine these mathematically and simplify down, which would be fine, because you can do some trig-based stuff and get around what sine 15 is and what cosine 15 is, and eventually get where you need to go. Or you can let your calculator do the work, because here in physics we like decimals because it's significant figures anyway. So just punch into your calculator, if you will, cosine of 15. In fact, you're going to end up needing to do that. But let me show you this. Let me work it out in more mathematical sense. Let me factor out FP. Does that make sense to everyone? Let me factor out FP. So now I have FP times, now you can punch into your calculator, cosine 15 minus 0.48 times the sine of 15. Let me get rid of that decimal there. Are you okay with that idea? Factoring out the FP, now you just got a bunch of stuff, a bunch of calculator. If factoring it out makes you nervous, it's not a big deal. Cosine 15 is a decimal number. You can just punch it into your calculator and it gives you what the decimal number of cosine 15 means. Okay? So then you can replace it with the decimal. Sine 15 is just a decimal. 0.48 is just a decimal. So you can punch in 0.48 times the sine 15, just get a decimal, throw it from the other FP. Okay? And then combine from there. That's not a problem. What is cosine 15 minus 4.8 sine 15 come out to be? 0.4884. Say it to me one more time, please.
0.8416.
Last step. 5. Those cancel out. Leaves you with FP equaling what? 6,000? 6,700 and what? 6,706 newtons. That looks about right.
You're like 6,900. I got 6,700.
Okay, 6,900 is a little off, but not too much. It could be around. It could very well be around. Yeah, storing versus rounding off what I have written up here. So let's come back. Let's look for sig figs. Scrolling all the way back up. 2 here, 2 here, 2 there. I get 2 sig figs. So this becomes what? 6,700 meters. Yeah, it's kind of long. Here's the point that I want to make to you about these problems. The physics of this problem was done all the way up here. As soon as you have written these lines, everything above there is the physics. Everything below there is algebra. Simple math. Now, yes, I'm making you apply all this math that you've learned throughout the years into one problem, but it's still just algebra. It's what you've done all your lives. It's not a problem. You can do the simple math, okay? The challenge is not to get freaked out. Just say, I know I can do it, not a big deal, system of equations. It takes me a long time, who cares? It takes me a short time, who cares? I'm just going to do it. Okay? So understand you are fully capable of this algebra. The challenge is believing in yourself that you can do it and then going for it and actually trying. Okay? Questions on this? All right. First step, no matter what, okay, is to go and do your free body diagrams after you got a picture, which I feel like we're going to be okay without a picture, right? Because there's what actually happens, right? It accelerates for a little while, okay? So I feel like we're okay without a picture right now. So free body diagrams, and you got to do the two separate. So for the cart, what forces do I have acting? Driving, going up, oh, excuse me, going down. Woo, boy. What else? Normal, going up, gravity going, let me go ahead and put that, and tension going to your right. Let me neglect friction. Okay, I've got my cart where it's pretty well oiled. We're going to neglect friction. Now we know that there's going to be some error in this, okay? We don't expect the accelerations to be precise down to the hundredths place, probably, because of friction. Okay, but they should be pretty close. So let me neglect that. How about for the hanging mass? What forces do you expect for the hanging mass over here at the end? Gravity goes down.
Would gravity be like the strongest force in the room? Would it be like the longest one in the free body diagram?
Not necessarily. Not necessarily. Here. Some of them will be of equal length. Some of them will be of equal length. And tension going up. Is there any normal force here? No, it's not on the surface. Now, divide everything into components. Nothing to divide into components, right? This next step is critical. You must choose system positive and system negative. System positive and system negative. Here's what I mean by that. Over here on the cart, let's choose up to be positive and down to be negative. Do you want right positive or negative? Positive. Now, think about the system. whenever the cart moves to your right, that's positive. Which way does the mass go? Down. So, down for the hanging mass must be positive, up must be negative. That's system positive, system negative. Let me say that again. Think about the entire system rotating. The entire system moving. We're going to call when the cart moves to the right positive, right? We're going to call when the system goes that way positive. Cart moves to the right, mass goes down. So if cart to the right is positive, down for the mass must be positive. The way I like to do this to make sure that I'm getting it right is, at least on my picture or on the diagram, follow the string, follow the rope. If I say, okay, the rope's pulling it to the right and that's positive, that means following it everywhere that the rope's pulling is positive. So positive, 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 positive. Okay? So system positive, system negative. Right? As long as you're doing that, you'll be fine. Okay? Next step. XY axis for both of them. Right, so over here for the cart, and the X axis, I only have one force, right? Tension, yeah. Tension equals MA. In the Y axis, I've got normal minus gravity equals the acceleration of the y-axis is 0. The cart isn't launching up into outer space, plunging down to the depths of the Earth. And just a little thought here, why do we really need the y-axis of objects normally? Find normal force that gets us to friction. And since there's no friction, I'm not even going to end up worrying about the y-axis of carts. Okay, I don't even have to worry about it. Over here on the hanging mass, all I have is y-axis, because there's nothing in the x-axis, and I got tension, I have gravity positive, tension negative. Scroll back up to my free body so you can just kind of confirm positives and negatives here. Correct. There is an acceleration in the y-axis of the hanging mass. I mean, it's actually accelerating down. And since they're connected by a rope, the tensions in the rope are going to be the same rope, right? And the accelerations of the two objects is going to be the same. That makes sense, right? I mean, if you attach two things with a rope, they're going to accelerate at the same rate. When was the last time that you can think of that you attached something to a car with a rope and you accelerated way off forward and the other thing accelerated much slower? Yeah, that's called a rope braking. Okay? Yeah, they have to go together at the same rate. Tension's the same, acceleration's the same. All right, let's start plugging things in that we know and try to solve for this acceleration. Over here, I don't even have to worry about the y-axis. We already said that because no friction, not worried about it. Tension equals the mass of the cart was 0.065. Sorry. Did I speak and wrote it right? Okay. Over here for the hanging mass, force of gravity comes mg, now minus t, equals ma. Mass, 50 grams, that's 0.05 times 9.8 minus t equals 0.05 A. And now, check it out. I have two equations, two variables. System of equations. Okay? System of equations. I got stuck on the left. I had T and A in it. I don't know either. So I went to the other one. Right? I didn't just jump to the y-axis. I jumped completely to the other object. Okay? Yes. Yeah. Keep jumping axes, if you will. Keep jumping until you get to something that will work. Right? If I jump to the y-axis here, all I would have found was normal equals mass times gravity, normal equals some number, and that doesn't help me at all. Okay, so I would have jumped again to the next one, continue to solve. Solve for one variable, substitute into the other equation. Which equation or which variable looks easiest to you to solve? Yeah, tension over here, right? I mean, it's already solved for, so let's use it. Yes?
Only the acceleration is the same. You couldn't use any other variable.
Well, the tension is the same too. Both the tension and the acceleration is the same because it's the same rope, right? I mean, if I pull with 500 newtons here, right, on this side of the mass, 500 newtons is going to be pulling on the cart on the other side, right? If it wasn't the same, that means the rope has to be stretching out, right? So assuming this rope doesn't stretch, assuming that it's massless, tension has to be the same in all parts of the rope also, okay? So tension and acceleration are the same. The easiest thing to do here is going to be to take this tension and substitute it in. Everybody see that? The easiest thing to do is, I've already got T equals MA, right? T equals 0.065 times A. The easiest thing to do is just take that tension and plug it into the other equation. You good with that? So now I got 0.05 times 9.8 minus 0.605 times A equals 0.05. A. I need to group my like terms. So let me add a 0.605 A to the other side. Right? 9.8 times 0.05 comes out to be what? .05 plus 6.05. 5. Oh, so one.
That's right. I'm pretty sure it's right.
Okay.
Because if they're moving twice, you put it in twice. Oh.
Line them up if you need to. Right. Divide both sides by 0.655. .748, you say. Now let's look at our actual measurements that we have right now to see significant figures. Although the error is going to be so much bigger than our sig figs, it's not really going to matter too much. But I got 3 sig figs in the mass, right? We can assume 9.8 is exact, so I get 3 sig figs here, technically with this. So 0.748 work. Now, let's actually test this. The more people who time this, the better. I pulled up. Now, let me show you something here. For the distance this car can travel, we aren't going to be going the full distance. We're going to go until this hanging mass actually hits the ground. So we're going to go from the hanging mass being pulled all the way up, right there, and then we're going to release this thing and let it go as far as it can. But check it out. The car conditions change, right? There's no more acceleration, right? There. We're looking at traveling exactly 70 centimeters. What do you know? So we're looking at traveling the distance S. .70 centimeters. What's the initial velocity of this cart? 0. What else do you know?
Acceleration.
Yeah, we're solving for acceleration. Here, we're going to check to see, and you're going to give me good. You're going to give me the time. Okay. you're going to give me the time. And we'll run multiple trials of this so we can get a decent average time going on here. We'll average all of y'all's. So stop it, whichever you can see better. Whenever the cart passes 70, or whenever the weight hits the ground. I'll try to actually say stop. Okay? On your mark, start from tomorrow. Yeah. On your mark, get set, go. Stop.
Got 1.3. Got 1.6.
All right, feed me these times so we can average.
1.3.
I got a 1.25,
1.3.
1.3, 1.32.
Outlier.
An outlier. Oh, an outlier. How about the rest of you? Give me some of these outliers. Give me some of these outliers. How bad?
1.65.
I believe it is. 1.6.
1.6. Okay, no, that's not right.
I had a 1.6.
A 1.6. What else? All right, let's try it again.
You yell stop. Yeah, I said that.
Your eyes are quicker than
You're not very good. You can count from 3.
I tried to play this time.
Yeah, like when you let go.
All right, here's 70.
Yell stop.
All right, I'm going to say 1, 2, 3, go. All right?
Wait, start on go.
Start on go.
Start on go or something?
1, 2, 3, go. Stop.
Okay, I think I hit the 1.3.
I got a 1.4. 1.39.
I got 1.6.
I got a 1.6. I got a what?
1.39.
Two 1.39s.
1.46.
1.46. 1.25. 1 point what? 1.38. All right, last round. Try it one more time.
What did we go? Oh no.
I actually enjoy looking
All right, here we go. Ready? 1, 2, 3, go. Stop.
Oh, I was late.
All right. What do I got?
1.46.
1.46.
1.39.
1.39.
1.3.
1.3.
1.39. Really?
1.5.
Yes, what?
All right, that's pretty good. Let's just
1.67.
1.67. All right, those 1.6s aren't too bad. If I'm going to guess, I'm going to say that they're outliers. So let's neglect those. Take those times right there. Somebody give me an average, please. You got 1, 2, 3, 4, 5, 6, 7, 14. 14 times, so add them all up, divide by 14, what do you get? 14?
How about what?
14. I'm sorry? 1.37?
1.37.
Alright, now let's do kinematics. Let's see how accurate our acceleration was. So, double check on that average. Sure good. And that sounds about right. Okay. What kinematic equation do you want me to choose from these variables?
Yeah.
S equals U plus AT? Okay.
That one.
That was going to be an interesting equation. Okay. So here's kind of our favorite kinematic equation. S.7. What's U here? 0. What happens to UT? Gone. Don't even have to worry about it. 1/2 A 1.37 squared. A is going to equal dividing the 1/2 and the 1.37 squared over 2 times 0.70 divided by 1.37 squared. What do you get for A? I've got one person who says 0.74. How about the rest of them?
Where did you get 2?
That's 2 times. If you'd like, if multiplying 2 and the numerator, dividing by 1/2 is the same thing as multiplying by 2, but I can move the 1/2 back down.
0.745.
Yeah, that's what I got.
How about that? So let's check our sig figs. I have from, and I didn't use my meter stick as accurately as I should have. I only gave myself 2 sig figs from the meter stick. So this would become 0.76 meters per second squared is what my acceleration is. Check it out. Nope, thank you.
We got the wrong one in here.
That's dead on.
Dead on. Dead on. Newton's laws work. Newton's laws work.
So confused.
I'm not.
How do you confuse that?
Questions on this?
Yeah, how?
How does what work?
What kind of magic does it?
There is no magic, just pure physics. Pure math and physics calculated. Well, yeah, we came out very, very precise here. So, how did we? Let me talk about how I kind of eliminated error down. First off, I put a large mass in the cart. That way, the acceleration isn't too high, so it gave you time to hit start and stop on your stopwatch. Okay. If it was too fast, you would be way off, right? Then I also had pretty much the entire class take the times. It gave me enough data that I could throw out outliers and then average it all to get to an even more precise number. And then we did it 3 times all over. I mean, I was able to throw out outliers and still have 14 data points to average together, right, to get a very good average time. So I'm reducing error all the way down, to the point that just using meter stick and stopwatches and being still a good ways away, but y'all are still at the desk, we came up with a very precise number. Okay? Okay. Next, let's work problem. We did. But,
Can we ask questions? Break time.
break time.
Yeah, can we have time? What do we
I don't like
attention? We only have like 4 minutes. What
So?
music can we use as attention? Basketball.